Hello everyone and welcome to our presentation. I'm Milad Tusi. I'm an interactive media master student at the University of Applied Sciences Upper Austria. On behalf of my co-authors Katja Gallhuber and Michael Lankes, I'd like to present to you our topic, digital puppetry utilizing extended reality technologies for animations. Character animation is a specialized area of the animation process which is widely used today in the fields of film, game, advertising, education, and the metaverse. Our work presents a character animation method to work with digital puppets using immersive technologies, and I'm going to talk about some challenges that will be tackled during the completion of the prototypes and the final results which help train beginner animators and reduce animation production costs. We have read several recent studies that have informed progress on animating objects and characters in virtual and augmented reality. Our main contribution is to explore the possibilities, challenge, and limitation of digital puppets in VR that could be beneficial for animation and games in future work. After we designed some mock-ups, we started prototyping based on our concept by using Oculus Quest 1 and 2 as a target device for tracking the full body without any additional pricey trackers. The headset is cost-effective for low-budget animation, and it is a standalone device with two 6 degrees of freedom controllers. No additional PC or console is required. Our first idea was to attach VR controllers to our shoes and track our feet and use the hand tracking options to track our hands, and finally the headset for tracking our heads. However, we failed because the controllers did not stay in the fields of view of the Oculus cameras if we attached them to our feet, so it was not a reliable solution. Then we decided to continue with our second idea and focus on bringing the long tradition of the marionette, which is called the string puppet in France, into virtual reality to investigate possible interaction design choices for digital puppets that could help build animation authoring tools for beginners in the future. The virtual low-poly scarecrow puppet and the wooden controllers are modeled and textured in Autodesk 3ds Max, and the final 3D model with the materials is imported in Unity as an FX file. The character rig itself is built in Unity, and each part of the puppet body is joined together with physics components like the character joint, fixed joint, and hinge joint. To achieve gravity, the rigid body components is also used. Following these, 5 spring joints are attached to the marionette head, hands, and knees. These are connected to wooden controllers as well to rig the strings. Afterward, the line connector script is written to render the strings in play mode by using the line renderer component. We discovered that it is more optimized than including geometry for the strings. The seesaw rotation script is written to imitate the body movement of a real-world marionette. The current position in the y-axis of the individual limbs is dependent on the degree of rotation of the control bars. By grabbing the wooden control bars and changing the rotation in the z-axis, individual arms and legs can be lifted or lowered. The project is implemented in the Unity and built for the Oculus Quest 1 and 2. To provide simple interactions such as locomotion and grabbing the wooden control bars, the XR interaction toolkit is used. After correctly setting up the Guardian system, which is responsible for defining the boundaries of the play area for the Oculus headset, the prototype can be used at any possible location where it is at least possible to fully stretch both arms. In this project, the user can navigate to the marionette in the scene by using the joystick of the left VR controller to interact with the puppet in play mode. A continuous movement was chosen as a type of locomotion since it would not be possible to create animations in which the whole puppet moves by teleporting from one position to another one. The final interaction design of the puppet is strongly based on the way how controlling marionettes in the real world work. To grab the wooden control bars of the marionette, the user can reach out for them and press the grip button of the controllers to hold them. With this design decision, the user can decide with which hand the controls for the legs or the hands should be grabbed. With a combination of changing the height and the orientation of the leg controller, a simple walk cycle can be created. By lifting or lowering the bar for the arms, the general posture of the puppet can be influenced. which makes it possible to animate the puppet in a standing, sitting, or kneeling position. By lifting both controllers, a jump can be animated. While gravity is applied to the body of the marionette, the wooden controllers are not affected by any physics, which makes it possible to easily release them and pick them up again from a different perspective. This decision aims to support the user since it is easier to look at the current posture from different angles, and it prevents tangled strings that would happen with a release puppet in the real world. In the early stage of designing, the puppet was rigged in 3ds Max. However, the rig was not reliable enough and the movement of the puppet did not feel natural with the bone systems in Unity. Therefore, the whole rig was built with physics components in Unity, which had a more satisfactory outcome. In other early approaches, interaction for controlling the puppet was designed in a more abstract way. By controlling the left arm and the leg with the left controller and the right arm and leg with the right controller. By mapping the activation of controller to the primary and secondary buttons of the controller, the user was not only able to control each limb individually, but also could decide when to release it again. However, pressing 4 buttons individually was not intuitive. Therefore, the implementation focus was changed to analog marionette controllers. Another design idea was to let head of the puppet follow the position and rotation of the headset. This worked very well, but led to the problem that the user could not fully release the whole puppet and control it from a different perspective. For this reason, the head was attached to the arm controller in the current implementation. During the prototyping of digital marionette in VR, we found a limitation of our prototype which becomes visible when the distance between the grab control bars becomes too high by fully stretching both arms. Since users can move their hands without limits and do not feel the stretching of strings like for a real-world marionette, extending these limits in the current implementation leads to undesired behavior. Since we still continued working on the prototype after the submission to this conference, we could also work on this limitation by restricting the movement of the controllers to the limit of the possible movement of the ragdoll. If the user wants to extend the wooden control bars further than the limit, the control bars will not follow the hands further, and haptic feedback in terms of increasing vibration of the controllers will inform the user that the possible limit is reached. At the moment, the control rig only works for humanoid puppet, but it can be easily extended for non-humanoid puppets. Future research will lead to 2 directions. The first direction will focus on building a low-budget animation authoring system in VR for people who are still new in animating characters and cannot afford expensive software and hardware. We plan to make a training scene to guide beginners on how to animate a simple walk or run cycle in VR and record their works. Then they can play the recording keyframes and walk around the virtual training room to see the outcome from different angles. Face puppetering can be added to the current setup by intuitively driving facial expressions with buttons on VR controllers. In the second direction, we would like to use the digital marionette in a future VR game. We are currently working on using the digital marionette in a VR game and want to investigate how the puppet's physics affects the game experience. A big inspiration for this research direction is games like QWOP, Octodad, or Goat Simulator that have challenging physically based character controls. We want to measure to what extent these challenging physics for controlling a character in a VR game contribute to the game experience. Overall, the lessons that were learned during this work may benefit animators, game designers, and researchers who also intend to bring analog puppetry into the immersive virtual environment. Thank you for your time, and we would be happy to answer some questions.